All right, let's look at question 9 from section 3.4. So we have a company designing propane tanks. So they're cylindrical with hemispherical ends. So let's figure out first what our objective uh, function is. So let's look for, all right, so I'm seeing the word minimum. So we want to minimize the cost. So that is going to be our objective function. What's the cost going to be based on? The cost is based on, so $5 per square foot on the hemispherical ends and $2 per square foot on like the vertical or like the straight sidewalls. So how do we find the surface area? Yeah, just really should draw a picture here. So base is like a pill. So if I want to find let's write down a couple formulas here. The surface area of a sphere, a full sphere, is 4 pi r squared. What about the surface area of the other side here? The other side of this is going to be a rectangle. So that's like if you were to take like the straight part of this between the two ends and unroll it, that would be rectangular. So that's just going to be a length and a width. So we should try to find a way to unite these things or relate these things to each other. So the cost of the spherical end, so I have two half spheres. That's going to be 4 pi r squared. And how much it costs $4 per square foot. I'm sorry, $5 per square foot for the ends. So for the spherical part of this, it's going to cost $5 per square foot there. And how about for the rectangular part? So what is going to be, now if I were to unwind this rectangle, so let's say this, that's the radius of this spherical end. And we'll call the height of this thing h. So if that's the case, then the height of this rectangle, or yeah, this dimension is h. How long is this? So that length is going to be the same as whatever the circumference of the circle is, so that'll be 2 pi r. So plus 2 pi r h, and that costs $2 per square foot. So my cost equation, or my cost function in terms of radius and height, is equal to 20 pi r squared plus 4 pi r h. All right, so I have a constraint here. I want a tank that will hold 1,000 cubic feet of propane. So that constraint is based on volume. So what's the volume of this tank? So it's still going to have spherical ends and um, a middle that's cylindrical. So what's the volume of a sphere? That is going to be 4/3 pi r cubed. What's the volume of the cylindrical piece? And I'll write down these formulas off the side as well. The volume of a sphere is 4/3 pi r cubed. The volume of a cylinder is equal to um, basically the area of the base. So pi r squared is circular base times the height. So plus pi r squared times the height. And I'm constrained to 1,000 cubic feet of volume. So I'd really like to combine these two. I think the easiest thing to do would be to solve the constraint equation for height because height only shows up in one term. So let's do that. So pi r squared h equals 1,000 minus 4/3 pi r cubed, or h equals 1,000 divided by pi r squared minus, what cancels out here? 4/3, the pi's cancel, so 4/3 r, I believe. Yep. So 1,000 over pi r squared minus 4/3 r. So having this constraint equation now enables me to write my cost equation in terms of radius only. So the cost is 20 pi r squared plus 4 pi r times 1,000 over pi r squared, not plus, minus 4/3 r. So before we take a derivative, we should simplify a little bit. 20 pi r squared plus, the pi's are going to cancel. A power of r is going to cancel, so I get 4,000 over r, minus 16/3 pi r squared. All right, so now I think that's as far as I care to simplify. So I want to optimize this, so I will take a derivative and try to find critical points with that. The derivative is going to be 40 pi r. The derivative of 4,000, so 4,000 over r is equivalent to 4,000 r to the -1 power. So that's minus 4,000 over r squared. And then finally, minus 32/3 pi r. And I want to set that equal to 0. All right, so how do we manipulate this? So one thing I'm going to do right away is I'm going to multiply the whole equation by r squared. And that'll help me clear out some of these values of the variable in the denominator. So if I do that, I get 40 pi r cubed minus 4,000 minus 32 over 3 pi r cubed equals 0. So now I can start moving things around. I'm going to move the 4,000 over. So 40 pi r cubed minus 32/3 pi r cubed equals 4,000. I am going to factor out an r cubed. So I got 40 pi minus 32/3 pi equals 4,000. Probably should have done this a long time ago, but I'm going to combine the 40 pi and 32/3. So what's my common denominator here? What's 120 divided by, or minus 32? So let's just replace it. So this will be 88 over 3 pi. So r cubed equals 4,000 over 88 over 3 pi, which means r is approximately equal to what? So let's get a good approximation. So I am getting a value of R 3.514. So I got a radius. So are we done? Not quite. We're there. We're close, but there's one more thing we got to do. So, and since this is the fourth one of these that I've worked out, hopefully I can leave this for you. This is the critical value of R. So how do I find the cost with that? Well, I have an objective function for the cost, which is expressed solely in terms of R. So if you find the value of 3.514, this right here will give you your minimum cost.